So, these 2 days will be about system modeling and the basics. Let me start by introducing ourselves. So, my name is András Vörös. If you want to say it in Portuguese, it is André Carvalho. I'm an associate professor from the Budapest University of Technology and Economics. I will give most of the lectures, but I have some help. Bence Groich will also make a presentation about state-based modeling, and if we have some time at the end, I also plan to show you some industrial case studies to motivate you to watch the presentations maybe again and use all these information in your work. And also, Vince Molnár is here. I'm not sure if he will give presentations, but he helped a lot in preparing the slides, and actually he's in the OMG standardization committee, so he's responsible for developing many of those system modeling tools that one can use. So this course will be about the fundamentals of system modeling. We will mainly cover the basics of modeling for software and systems engineering. We will talk a little bit about structural models and state and process-based models. If we have time, we will also talk about model validation, model verification. And if anybody is interested, we can give some more materials, more advanced materials, so you can also learn at home. So let's start by the foundations of modeling, and I will start motivating example. I do not know if you know this video game. Actually, this is quite old, so many of the participants, I guess, will not know it. But why I mentioned this small car game from the 90s? It was a car racing game, and what was very interesting in this game, it also supported track creation. And in this sense, this game was the first that applied some kind of domain-specific modeling, in the sense that it was provided for the users, and the users can themselves use this domain-specific model. So this is how it looked like. So in the right side, one can just choose the tracks and build a complete racing track from the building blocks. And this was the first game where one can build all these things. And so the engineers, the computer scientists, had to think about what kind of language to use to define these car races, and especially the complete tracks. Also, they had to think about that what kind of behavior should be prohibited, or can be omitted, or can the users let to be used. So many questions were raised, and during the when one person was just developing the track system. So, for example, with which car can one go through all these tracks and all these elements? It is also a good question that if it is the well defined the track, so if it is correctly put together. A good question also raised that which elements may be combined, and which combinations can be created. And also, can I drive along a track in the opposite direction? Because, you know, when somebody uses a game, everybody is just looking for some tricks and to use the software in a way that was not intended by the developers. And also a good question, if the track is realistic, is it good to race on this tech in this track? And on the right hand side, in the track editor, one could use the elements, but when I'm developing a modeling language, and that's definitely some kind of modeling language to develop these car games, the need to add new type of elements is not naturally raised. So anyway, I just wanted to show this small example to show you that, okay, modeling is not just about those diagrams that we use, but when you go where right now.
Way better now. Thank you so much.
Okay, so I will just repeat that what is a model, because I think that's a very important thing. So the sciences do not try to explain, they hardly even try to interpret, but they mainly make models. By model is meant mathematical construct, which with the addition of certain verbal interpretation, and that's very important that verbal interpretations are needed. So it describes some observed phenomena. So the justification of such mathematical construct is solely and precisely that it is expected to work. That, what does it mean? That it correctly describes the phenomena. And it also must satisfy certain aesthetic criteria, because it must be useful. And who told this? Actually, you might heard about John von Neumann. He's a very famous Hungarian American mathematician. So that was one of the first definitions of models that we also use today. But we also have to talk about the differences of scientific and technical models, because I'm an engineer, so I will definitely use technical engineering models. And in some sense, scientific models are different, because scientific models are wrong if they do not fit the real world. So actually we cannot use the Newtonian laws inside the black hole. It will definitely not work. On the other hand, we can say that technical models are never wrong, because if there are discrepancies with the real world, that means that actually the implementation is wrong. So the main difference of scientific versus engineering models is that scientific models are used for describing, and that's very important, describing the world and different phenomena. And engineering models are used to prescribe, so to define how what we engineered should work. So if you just take another example of value of models. So in science, the value of a model lies in how well its behavior matches that of the physical system. In engineering, the value of the physical system lies in how well its behavior matches that of the model, because we want to implement in the physical system what we engineered in the model. So a model is defined as a partial and simplified depiction of a real or a hypothetical world that is actually the system. And what is important that it can be substituted. So this system can be substituted for specific viewpoints. So the important questions, what we have to decide and have to answer when modeling. So which part of the world do we want to model? What should we simplify? And how it can be mapped to the real world. And this will also define when it is possible or recommended to use. So when our models are applicable. Because anyway, it's sure that they will have restricted applicability, so they will not solve all the problems. And the benefits of using models is that it used to have smaller, it used to be smaller, and it has manageable size compared to whole systems. And I will just go into the details when it is useful. So, what is not a model? I do not know if you have already seen this drawing, but I guess actually it is a French drawing. I cannot understand without translating the text on it, but maybe in the audience there are more people who can read it. So anyway, what is there is that this is not a pipe, because this is just a drawing of a pipe. So the model is not the reality. And in many cases, people think that, okay, the model is just a diagram, but the diagram is not a model. The diagram is just a view of a model. As also you can see in this drawing, that's just a view of a mental model, actually, because it's in our head. And also we will talk about later that in this picture you can see that there is a model, actually drawing of a pipe, but there is also drawing of that drawing. And so the models can have their own models, and this can be stacked on each other to be able to define modeling languages, and then using these modeling languages to model the real world. And also an important part of modeling, here you can see abstract drawing. I think many of you have already seen this. So it mainly contains a really infeasible situation when the water is just going up, going down, but this will not happen in real life. So what we can see here is that we used this, so we just draw this drawing that is actually correct in the sense that it is a drawing. So we used the syntax correctly in the sense that, okay, it's a drawing, just we used lines and other things to construct this drawing. But this model is not realizable. So in reality, it will not work. So even if we use the correct syntactical elements, then we might still end up in a model, in a, for example, in this case, a physically infeasible model. So a model, it can be used also for analysis. So when we are just looking at this drawing, or if we just put into a physical simulator, we could conclude that, okay, it will not work in this way. So there are many important properties and functionalities that models can provide for us. So in one hand, we can have mathematical models, and on the other hand, we have the real world, and we use these mathematical models to answer questions. And what is an important thing, that models are usually work in a closed world thinking. So the effects and factors are just valid inside the model. Also the parameters. And the models have no defined behavior outside of its scope. So if I have a model, it will definitely not define other parts of the world. So it has just limited responsibilities. And there is also some parts that we cannot really model, for example, human decisions, or there are many ways to support modeling when we don't want to model something explicitly. For example, when we are generating models. And by using models, we can validate solutions, and the models and mathematical models especially are constructed to answer questions. So, for example, if we are working in the industry and we are producing things, then a mathematical model can describe if we have enough materials to produce some products, and we want to answer with these mathematical models that all of the orders can be completed in time, and we can have also a goal, a target function to minimize costs, and we want to avoid the situation when we do not have enough materials, and this way we want to fulfill as many as possible orders to be completed in time with a minimal cost. And why I'm mentioning this model? Because I'm sure that many of you are familiar with physical models, because I think here in IMPI there are many physicists, but these models can have such economical usage also, for as in the example. And a few years ago, our research team worked on a project where actually we had to create models for such production systems. And what I also wanted to mention here is that finally we ended up on a solution that was actually not designed by us. It was a neural network that learned all these parameters and computed the results. So sometimes models are created from data, and sometimes actually these are not useful models in the sense that in many cases you cannot really interpret them, but they could model the real world quite well. So these are also models. So as you could see in the example, the model is a means for answering one or some specific questions. So all these models have some goal. And I will also show another example, some other example of modeling when actually modeling went wrong. This example came from the avionics industry, not the Boeing example. I could also bring that one, but there is much earlier example. So the braking of an airplane uses actual
wheel brakes and the thrust. This is the thrust. So when you use the power of the engines to stop the plane, and it's very important. And the logic was that behind the behavior behind in the software that engineers just developed, that we can just brake and use this thrust if we are on the ground. So how do we know that we are on the ground in the case of an airplane? Okay, if we have load on both wheels, or one wheel is rotating fast, so at least one wheel is on the ground, and yeah, in this case the load will not be so big because the half of the plane, let's say, is still in the air. But if one wheel is rotating fast, then we can use the thrust to stop the plane. And they wanted to avoid the situation when the thrust stopping, the thrust braking starts in the air, because it's very, very dangerous. So when the Lufthansa flight just departed to Warsaw, there was a big wind and also rain. So actually one set of wheel just arrived on the ground, but they were sliding, so they were not rotating. And the other wheel was still in the air because of the wind, and the pilots couldn't use the thrust system to brake, and this caused an accident. So in this case, what we expected from the world and how we imagined and designed our models, it was not correct. It was not describing the real life correctly. And actually, so far, this is a very important question for the avionics industry in many, many cases. If you remember the the problems with the Boeing airplanes, that was also related to the situation when engineers didn't think about some cases, some corner cases. So anyway, this is an example from real life. Sorry, I cannot go on. So in the reality, unfortunately, uses open word, but model is a closed word. That means that only those assumptions can be taken into account that we have in the model, and that can really cause problems, because if we don't have enough assumptions and we didn't take into account all the external things, then our models will need not be faithful. And also the conclusion is that the implementation of a bad model can be deadly. And I want to bring another example from the Second World War, when a very famous mathematician, Abraham Wald, he was just working on where to put the armor on the planes, and they used statistics for that. So when the planes came back from bombing Germany, they found that this in the figure below, the red dots show when the planes were hit, and they were just thinking about, okay, where to put the more armor. Yeah, well, we should put where there are more injuries of the planes. So that's quite it seems quite logical. But indeed, Abraham Wald showed that, okay, this approach doesn't take into account the reality, and the reality is that those planes with these kinds of hits actually came back. and those planes with the white area, they didn't come back. So we should put the armor there because we want more planes to come back from the fight. So an important takeaway is that a model is only valid with its environment. So even if I see the statistical distributions of the hits on the plane, I have to take into account what happened and what is our environment. Otherwise, I will make bad conclusions. Actually, this was the same in the First World War when the Austro-Hungarian army just introduced new helmets, and there were more injured soldiers, and it turned out that it's not because the helmet is not good, but it was because they survived, so they were injured and not dead. So this kind of survival bias and many other things can really make the development of the conclusions of the different models easy. So let's go through the purposes of the models. So I'm sure many of you have already used modeling in real life. Actually, there is a Scandinavian company that is quite popular in Hungary. I do not know. I guess there is also in IKEA here in Brazil, and they introduced web-based kitchen designer, and that's also a kind of modeling tools, and it shows that modeling is very good to try out several options. So it's much cheaper to try out in this web-based kitchen designer the different design alternatives of our kitchen than buy the things and shuffling the furniture and then find out, okay, I don't need this chair and that table and so on. So, and why I mention this is that when we work together with the industry, and we actively working with right now the automotive industry, but I will also tell other examples, they also used modeling for that purpose. So in a project, what they wanted to know is that which design alternative to choose to still satisfy the requirements of the standards, but to choose the cheapest design alternative, because then they can have more profit. And in a project, for example, we evaluated, let's say, 40 or 45 different design alternatives, just let's say in a couple of hours. And we could compare them, and they were really happy that they didn't have to implement the most expensive and the most complex one, because a simpler one was still provided enough safety. But also another example, I'm sure that many of you know, at least have heard about hardware description languages such as VHDL or Verilog. And actually, these languages are also modeling languages. They are domain-specific modeling languages where the domain is the hardware industry. But it's not just for the hardware industry, but one can also use models to describe software or complete systems, and actually anything else can be modeled. And what is the point of modeling? So I'm a software developer, and many of the software developers used to ask, should I do modeling? And the reality, the situation is that yes, in fact, everybody already does, because when you write the source code, it's also kind of model. So it seems to be the implementation, but anyway, source code is a high level, is still a high level description, even if you use C, C++. For example, in the early 70s, when in NASA, they were just talking about, okay, writing assembly and low-level computer code, we should just change to high-level code like C. And many of the engineers said that, okay, it will never work. Why should I use such a high-level language? And so it's quite funny because 50, 60 years ago, it was seemed to be a high-level language, and we forget it now. And in many cases, we just consider these languages as low-level implementation. But no, they programming languages have also their syntax, and they can be used to describe what on the computer is running. Also, another very important thing is mental models. And what is a mental model? Mental model is what we have in our head during the development. In many cases, we don't draw on paper or in our computer, but when we are developing software, we always have some mental models. We imagine how our software should work. So you cannot do software development without modeling. And a very important question is that when should be these models documented? Because yeah, it's also an effort. So people don't like to document, people don't like to model, but in many cases, the role of the models is to help communication. For example, in human communication, or for example, when a human communicates with the machine, because when you just put your code there, that's also kind of model, and you give it to the machine and the machine will process it. But also, models are used in machine communications. So when you are using different communication protocols and so on, then you have a description of the information, and that goes from machine to machine. But also, human to human communication is not only important when we are talking about different humans, but also if I want to communicate with my future being. So I use documentation to help, let's say, in a couple of months, couple of years, to help myself to understand what I did 5 years ago, let's say. So why we implemented, for example, this algorithm this way some years ago. So the purpose of a model is to help communication. So understanding of the model is necessary. That's why we definitely need education. And what we realized in projects with the industry is that, unfortunately, if people are not educated how to do modeling and how to understand models, then the projects will not work. So every time, but I guess you can imagine, because you cannot, for example, do computer programming without knowing the syntax and getting to know the programming languages themselves. So what we need is modeling languages that can be used to describe, and that should be taught how we should understand these modeling languages. And what is a modeling language? It has a syntax which will answer that how do I describe the model? So how do I describe the model? That is the syntax. And it has some mathematical structure that is called the abstract syntax, and that will represent our model in a mathematical way. And to this mathematical syntax, to this representation, we need a notation. So, for example, we must have some graphical symbols in case of graphical models, or some kind of textual format. For example, in the programming languages, I will use textual format. I will write them textually. So that is the notation. And for one abstract syntax, so for one modeling language, one can have more different concrete syntaxes. So we can even combine them together, the graphical and the textual. And tomorrow, actually, you will see some examples for that. And also, very, very important question is the semantics. The semantics answers the question, what does the model mean? So, for example, I have the syntax like C, C++, System C, or whatever you want. And the question is, what does, for example, I++ mean? And also, many other things come with a modeling language, such as constraints, so that we can check the well-formedness of model, and we can also check the syntactical correctness, and we can also provide design conventions with the modeling languages that will just drive, for example, a team how to use special modeling languages for certain purposes. And I have already talked about the models of a modeling language, and let's go back to the first example in my presentation. So we have the concrete track. That is a model, a concrete model. And what we have in the right side is the possible track elements, actually the meta model that can be used to construct our model. So we have our meta model describes the different elements that can be used during the modeling. So a little bit more formally, the meta model is also a modeling language, and it will define what are the types of the objects, and what can be the connection between the objects, and how the types can be related to each other. So here, the meta model will define which elements, which track elements can be combined together, for example, and which elements can be used in building a concrete track. So the meta model is a model of a modeling language. Well, and the question can be raised that, okay, will meta model also have a modeling language? Yes, this can be just stacked on top of each other. So there are many different layers of modeling. And just to show some examples, so for example, in a database table, the meta model is the relational database scheme. In an XML document, the XML scheme is the meta model. In a relational database, then the entity relationship model will be our model. And if I consider an UML object diagram, the meta model is the class diagram, so it will define what kind of objects I might have. And I'm sure many of you are familiar with C++ programs, so the definition of the C++ language itself is the meta model, so it will just tell you what kind of elements you can use. But actually, models are not just used in computer engineering. So in many other engineering jobs use models. Architects, mechanical engineers, civil engineers, electrical engineers, landscape architects, and so on. So in these jobs also models are used for describing concepts, describe our system. That is, when we are drawing the models, we can still refine these descriptions. Then we can add further details in the dimensioning phase. You use model analysis and simulation to check if your model is good, and then you have to implement everything, and that's all common in these domains. And just to show that models are widely used in all phases of the system design process. So, for example, at the management phase, in the system design phase, product development and quality check phase, we all have some kind of models to support the engineering tasks, and these steps are usually supported by models. So just to show an example from a computer game, Portal 2, actually, I do not know how many of you know it, but just to show that I have the concept phase, then I can use models for the system design, for the product development, and finally I got something. And as you can see in this picture, that is definitely not what I imagined in the beginning. So we also have to talk about validation and verification. Validation is when we ask if we are building the right product. So is that what our consumer wants? And in the verification, the question is that if we are building the product right. So in this simple case, actually not this was what we wanted to do, but this small robot. So you can see the difference. So validation and verification is really important, and they are both supported by models in the engineering domains. And a very important application of the model is the documentation. So many companies mainly use models for documenting their system, and actually they don't use it for other poor purposes, because the model is simple to handle, it is easier to communicate, and it can be refined stepwise. So from step to step we add more information, and we can always focus on the actually important parts. It can be used for communication. It supports also visualization, because most of the models have some visual representation, so we can use it for demonstrations. It is mainly easy to understand if you have some textual language, not all textual languages, but many. And we can have expressive diagrams to help communication. And it really supports conceptualization and design. So it's kind of thinking tool. And I wanted to show you a famous picture of using software code as a documentation. I'm sure that you have already seen this. Many of you have already seen this picture. It's the source code of one of the first spacecrafts in paper. So the code can be used also for documentation, but I'm sure that none of you want to read all these pages, and you would just need some other description to understand. And a very, very important application is analysis. And I will, if we have time at the end, I plan to show you some analysis case studies. There are many different methods to analyze our models. The most common is reviewing and using static analysis. Static analysis is when we don't want to execute the model itself, but let's say we try to find patterns in the models, and these patterns can be best practices or problem descriptions. A more complex analysis is dynamic state space exploration, when you are executing your model. And if you traverse all the executions, so all the possible behaviors of the model, that is called model checking. And we can also prove theorems about our models that could be used to show that our models are correct. So our goal with analysis is detecting errors. It's usually best effort work. We might also try to prove safety properties, but that's a much stronger requirement. That's much more difficult to do that. And we can also use our models to calculate properties, such as, for example, timing and so on. And models can also be used for simulate. For example, to show that, to demonstrate that how our system works, and it really helps in understanding each other. It can also be used for some kind of validation. So I can validate if I built the system correctly. Did I build the right system? So I can also, when I have models and I do some kind of simulation, that can be shown even for the customers, for the stakeholders. And we can use this kind of simulation for experimenting to prove the desired system characteristics. We can also use the models for measurements of quantitative properties. And as I mentioned formerly, we can also substitute expensive real-life experiments. So, for example, in the kitchen example, you could just take a look at on your kitchen, on your display, and you don't have to build the whole kitchen. And it can also, an important application of simulation is when we have such properties that cannot be predicted using formal methods, different formulae, and so on. And we can also use models to automatize, to make some steps in the engineering process automatic. For example, if I had a model, a software model, then we can generate program code from that, and we can also use it to analyze the language. And we can add another model that will be a refinement of the original model, and we can just use it in the next design phase. So when I'm thinking about design phases in the development, then they will just represent different abstractions of the systems, like the models that I'm creating. And I add more and more information during the development. And also an important thing is that these models used to be really complex. So sometimes I had to create a simpler model from a difficult model to show some partial view that shows only the necessary information for me. And we can also use models for model integration purposes. So that can also happen that I have different models and I have to integrate them together because in the next phase I need them together. And just to show an example, for in the left hand I have a small model snippet of a state machine that I used to define the calculation of an absolute value. And what I have in the right hand side is the code generated from this small model. But there are many other examples, so we can use these models for web application development. When I just design some kind of database model, data model that I use in the web applications, and I can generate quite a lot of things from such a model. For example, in the right side there is a form with some buttons and some input text fields, so it's quite easy to automatize such, for example, in this case, a football application. I know that it's quite relevant in Brazil. I also used to play football with the guys every week here. And another example is smartphone app development. Here you can see a process, and this is a process that is used in an application, and it is defined with the help of some easy to understand models, and you can see the different steps in this project. And so you can use this very simple description to define how the steps are coming after each other. But also models can be used for reverse engineering. So if I have a source code, in many cases I need some models for the documentation, for documenting, and so in many cases this is also supported by models. And one example that I mention, because you will see it in a demonstration, is the Yakindi Statecharts. That is a modeling tool that the models that you create in this tool can be used for validation, simulation, code generation, and consistency checking. So that can also happen if you have good modeling tools, that you get so many things all together. And let's take a closer look at on some basic concepts and basic definitions. So in systems engineering and systems modeling, a very important thing is that we have our system that is interacting with its context, but the context will not be modeled, and this interaction happens through interfaces. In systems engineering, you can describe the system black box or white box. So whenever you can look the details inside, or when you cannot see anything inside. But whenever you are designing a system, you will definitely have to define the system inside. And the basic concepts are here that I will use different components and their interactions to describe the inside of my system. And what I have here as a powerful tool is refinement, when we are adding further details to the model while keeping the input model as an abstraction of it, and that's no contradiction. And the inverse to the refinement is abstraction, when I just hide some details. So in this example from the system, I used refinement when I defined the components inside. So let's make so we just actually used the refinement of the boxes. We will define this refinement relationship and abstraction relationship in the modeling languages in more detail. And many aspects can be refined. For example, we can just partition set of variables, a set of values of variable. So for example, if I have the two values of a variable, that good and bad, a good refinement, a good partitioning is that a good case is if I have it's either fast or average, but it's bad if it is slow, incomplete, dangerous. But it's just a very simple example. But also if I have armchairs and at a high level of abstraction, I can define, for example, the colors of these armchairs, or I can just define if they have armrest or not. But if I use refinement and I provide much more details, then I can even define many more things, such as, for example, in this example, the roller types or the structure of the backrest, and many more things. So this is a kind of refinement of a chair. And how do we do this kind of partitioning? So we map the disjunct subsets to elements of a set. So if we consider it formally, that will the definition is below, but what it means is that if I have different elements in the abstract domain, what after the refinement, those elements that are the refinements of the abstract elements, they will be in different subsets, and that is what is stated here formally. I will not read it because I guess you get the main points. So when I define abstraction, I can say that the abstraction is correct if to each element of the original system, an element of the abstract system can be assigned. So here in the side of B, for each element, I have to find the corresponding element in the left side in the domain of A. And an abstraction is complete in terms of a given property. If each property of the system is kept that is relevant for the given property. So that means that our abstraction is complete if it is property preserving. So it will not bring such information that will make our property, that will change the property of the system. But there you will also see some more examples to that later. And I just want to finish this part with some examples that when we used modeling in projects. So very nice domain was when we use modeling for testing robotic systems, autonomous robots. And in many cases, people do not know, cannot imagine if how one can use models for robots, because it seems to be quite different domains. But we did it, and actually later We also applied the same techniques for the analysis of autonomous systems, ADAS systems. I brought also another example because it's quite relevant here in Brazil, because I'm sure that you all know Embraer. That's avionic company. It's one of the biggest avionic companies in the world, and they are using modeling extensively. And we developed a tool for them to support the hardware-software allocation in avionics architecture. And they had a huge problem because an airplane, it has many components, so they had huge models, and they really needed this tool support to allocate and to solve this problem, to allocate these elements to each other. And it was even integrated into the development environment of Embraer, and I think they still use it. A recent development was when we were included in the development of a steer-by-wire system, where we actually applied model-based development of the full system. And why I mentioned analysis before is that in this case, the analysis could reveal real weaknesses of the system. So they finally fixed the issues. They had to fix the issues because their system was unsafe. And in the former project I mentioned, what we did with Embraer, actually, we didn't know details how they used it because we just had toy examples. But in this automotive domain, we had the real system working, and we found errors in the real system. Actually, the situation was quite similar to the Boeing case because it was a sensor fusion application with many sensors, and they had to provide many safety properties, and the model was quite similar to the one that what the engineers of Boeing should have done. And the analysis was quite similar that the engineers of Boeing should have done. And I also wanted to mention our last example is when we used modeling in the development of a new generation railway interlocking system, where we developed the domain-specific modeling language to support the engineers. And we also provided a verification, formal verification that revealed some problems that they had to fix in the design. And we also provided test generation support. And actually, in this test generation support, we are also plan to work here together with a professor from ITA and from IMPI. So if anybody is interested, just drop us an email, and anybody's welcome in the project. And what we do is also in this railway interlocking system example is reliability analysis, because that's also very important for the railway industry, and that was also the reliability analysis was done completely in a model-based automatic way. So let me finish with these examples. Actually, we plan to continue in 10:15, so I think we can stop the recording, and if anybody has questions, I'm here to answer the questions, and I'm really happy if we can talk about what I showed you. So, do you have any questions? I think it wasn't a complex presentation, it's just the introduction. Okay, then let's continue at 10:15 with structural modeling. So I will just stop the presentation now, and everybody is welcome in 30 minutes. Oh, I got a question. Is ATL still used? Yeah, ATL is a model transformation framework, and it is still used by some people, but that's not the, how to say, the most modern language for model transformations. But I haven't used it, so I must admit you that I do not know it so much. But what we see in the industry, that they started to use different approaches, different technologies. Thank you very much for the question. It was a very good question. But you can also ask after the next lecture. So see you in half an hour, and thank you for staying, and I hope you enjoyed the introduction. Thank you very much.